CCD sensor. This is where modern digital photography began. The charge-coupled device sensor was the dominant technology in cameras for decades, and understanding it explains why everything that came after was built differently. A CCD works by capturing light across its surface, and then moving that captured charge across the chip in a very organized, sequential way before converting it into an image. The result was exceptional image quality, clean colors, low noise, and a level of accuracy that made CCD the standard in professional cameras, scientific equipment, and early digital photography. The trade-off was power consumption. CCD sensors drained batteries quickly, generated heat, and were expensive to manufacture at scale. As smartphones entered the picture and the demand for smaller, cheaper, more power-efficient sensors grew, the industry needed something different. CMOS sensor. This became that something different. And today it is in virtually every camera you have ever used: your phone, your mirrorless camera, your laptop webcam, your dash cam. CMOS stands for complementary metal oxide semiconductor, and what made it revolutionary was not image quality alone, but efficiency. Unlike CCD, a CMOS sensor converts light to an electrical signal right at the pixel level, which means it processes data faster, consumes far less power, and can be manufactured using the same processes used for computer chips. Early CMOS sensors had worse image quality than CCD, but decades of engineering closed that gap entirely. Today's CMOS sensors produce images that surpass what CCD ever achieved, while fitting inside a device thinner than your finger. BSI Sensor. Once CMOS became the standard, engineers started asking how to make it better. The answer came in the form of backside illuminated technology, commonly called BSI. In a traditional CMOS sensor, the wiring and circuitry sit on top of the light-sensitive layer, which means some incoming light gets blocked before it ever reaches the pixels. BSI flipped the architecture literally. By moving the wiring behind the light-sensitive layer, more light reaches each pixel directly. The improvement this created in low-light photography was immediately noticeable. BSI sensors became the reason smartphones started producing usable photos in dim environments, in restaurants, at concerts, in situations where older sensors would have struggled badly. Almost every modern smartphone camera uses BSI CMOS as its foundation. Stacked sensor, BSI solved the light problem. But as cameras got smarter and started processing more data, faster video, real-time computational photography, 4K and beyond, a new problem emerged: processing speed. The stacked sensor addressed this by adding a dedicated processing layer physically beneath the image sensor itself. Instead of sending data off to a separate chip and waiting, a stacked sensor processes information almost instantly because the logic layer is right there, bonded directly to the pixel layer. Sony's Exmor RS was among the first to bring this to smartphones, and it enabled features that were not possible before: slow-motion video at extremely high frame rates, faster autofocus, and the kind of real-time processing that modern computational photography depends on. Quad Bayer sensor. When smartphone manufacturers started racing toward higher megapixel counts, a practical problem appeared. More pixels in a small sensor means smaller individual pixels, and smaller pixels capture less light. The Quad Bayer design was the solution the industry landed on. It arranges 4 pixels in a 2x2 cluster and treats them as one large pixel in low light conditions, combining their light data to produce a brighter, cleaner image. In good lighting, those same 4 pixels can be read individually, capturing the full high-resolution detail. This is why a 200 megapixel phone camera does not always shoot at 200 megapixels by default. It is often binning those pixels together for better quality. The Quad Bayer approach became the standard architecture in high-resolution mobile sensors from Samsung, Sony, and others. Micro Four Thirds sensor. Moving beyond smartphones, sensor size becomes one of the most important variables in image quality. Micro Four Thirds is a sensor format developed jointly by Olympus and Panasonic that sits between a smartphone sensor and a full-frame camera sensor in physical size. What it sacrificed in size compared to larger formats, it gained in portability and lens compatibility. The Micro Four Thirds system created an entire ecosystem of cameras and interchangeable lenses built around this specific sensor size, allowing photographers and filmmakers to carry professional quality equipment without the weight and bulk of larger systems. It became particularly popular in documentary filmmaking and travel photography, where image quality and mobility had to coexist. APS C Sensor. One step larger than Micro Four Thirds, APS C sensors became the standard in entry-level and mid-range interchangeable lens cameras from Canon, Nikon, Sony, and Fujifilm. The name comes from Advanced Photo System Type C, a film format from the 1990s that the digital sensor size roughly approximates. APS C delivers a significant jump in low-light performance, dynamic range, and overall image quality compared to smaller sensors, while keeping camera bodies and lenses at a size and price point that remains accessible. Fujifilm in particular built an entire professional ecosystem around APS-C, arguing convincingly that for most photography, this sensor size delivers everything a working photographer actually needs. Full-frame sensor. This is the format that professional photographers have historically pointed to as the benchmark. Full-frame sensors match the dimensions of a traditional 35mm film frame 36 by 24mm, and the size difference compared to smaller sensors is not subtle. More surface area means larger individual pixels, which means more light captured per pixel, which translates directly into better low-light performance, shallower depth of field control, and wider dynamic range. Full-frame cameras from Sony, Canon, and Nikon define the professional photography market. The trade-off is size, weight, and cost, both for the camera body and for the lenses designed to cover the larger sensor area. For decades, full-frame was the ceiling. Then medium format reminded everyone that there is always a ceiling above the ceiling. Medium format sensor. Above full frame sits medium format sensors significantly larger than 35mm, originally derived from medium format film photography. Cameras like the Fujifilm GFX series and Hasselblad use these sensors, and the images they produce have a quality and tonal depth that is genuinely difficult to describe without seeing it. Shadow detail, highlight retention, color gradation, everything has a smoothness that smaller sensors approximate but never quite match. Medium format was historically confined to high-end commercial and studio photography because of its extreme cost. Digital medium format brought that capability to a wider group of professionals, though it remains far from mainstream. It represents the upper boundary of what sensor technology delivers in a handheld camera today. 1-inch sensor. Back in the compact camera and advanced smartphone world, the 1-inch sensor became a significant milestone. The name is slightly misleading. A 1-inch sensor is not actually 1 inch across, but the format is substantially larger than typical smartphone sensors and small enough to fit inside compact cameras and, eventually, high-end smartphone camera modules. Sony's RX100 series popularized the 1-inch compact camera category, and phones like the Sony Xperia Pro I and certain Xiaomi flagship models later integrated 1-inch sensors into their primary camera systems. The jump in image quality from a standard smartphone sensor to a 1-inch sensor in real-world conditions is one of the most immediately visible improvements in mobile photography. Global shutter sensor. Most camera sensors use what is called a rolling shutter, which reads the image line by line from top to bottom. Fluent. In most situations, this is invisible, but when photographing fast movement, a spinning propeller, a fast-moving athlete, a subject under flickering artificial light rolling shutter creates a distortion where straight lines appear to bend or wobble. A global shutter sensor reads the entire frame simultaneously, eliminating this problem entirely. Global shutter sensors have existed in professional video and industrial cameras for years, but putting one in a consumer camera while maintaining acceptable image quality proved